Welcome to Aero Engineering Thermodynamics solved problem from the unit Basic Concept and First Law of Thermodynamics. Myself N. Venkatesh, working as an assistant professor in the Department of Aeronautical Engineering, SNS College of Technology, Coimbatore. Yeah, here is the problem. Is first one is principle of first law of thermodynamics, concept of heat transfer, work done, and change in internal energy. Here is in a non-flow process, there is heat transfer loss of 1055 kilojoule and an internal energy increase of 210 kilojoule. Determine the work transfer and state whether the process is an expansion or compression. Here is the solution part. Before we are going to the solution part, we will identify what are the given data from this given problem. Here is heat transfer is given. Its Q is equal to 1055 kilojoule and internal energy increases. It means del U is a 210 kilojoule, and the to find is work transfer. That means W is equal to what, and what is the process is an expansion or compression. Here is the solution. In closed system for which the law of thermodynamics applies. So here what is meant by a closed system? It means the flow properties will be interlocated in that systems only. So from the first law of thermodynamics, Q minus W is equal to del U. Here is the heat transfer and W is means work done and del U is a change in internal energy. So from the given data, Q value is 1055 kilojoule and del U, that is change in internal energy value, is 210 kilojoule. So we find work done from this given equation. Hence we substitute these values in the first law of thermodynamics equation. Q minus W is equal to del U. We get the answer W is equal to minus 1265 kilojoule. Since the negative, it must be a work input, so the process is a compression. From this problem, finally we find what is that work done value and the process is expansion or compression. This is the application of first law of thermodynamics problem. Hence we are equal to find what is the problem we will tell in that second one. In this problem, in a non-flow process carried out on 5.4 kg of substance, there was a specific internal energy decrease of 50 kilojoule per kg and a work transfer from the substance of 85 kilojoule per kg. Determine the heat transfer and state whether it is gain or loss. It is the another problem of the application of first law of thermodynamics. So similarly we can first find what are the given data and what are the sections to find. From the given data, its a mass will be given. It is a 5.4 kg and there was a specific internal energy decrease, that is means del U 50 kilojoule per kg. Here it indicates a decrease, so we are give the negative values. So the change in internal energy is minus 50 kilojoule per kg and the work transfer of the substance is 85 kilojoule per kg. So the W is equal to 85 kilojoule per kg. Determine the heat transfer and state whether it's a gain or loss. Okay. From the solution part, in a closed system for which first law of thermodynamics applies, the equation is Q minus W is equal to del U. It's indicate Q is equal to heat transfer, W is equal to work done, del U is equal to change in internal energy. We are interlocated this equation. Q is equal to del U plus W. We are substituting these values of what is meant by del U and what are the values from the given data, and same also applicable to what is the work done value. Finally simplify this equation, we will get 189 kilojoule. Since the heat transfer Q is positive, it implies heat is entering the control volume. So the process and state, it is gain. This is the next problem of first law of thermodynamics during working Stefan engine carried out of the system was 150 kilojoule per kg of the working substance. If the work done by the engine is 250 kilojoule per kg, determine the change in internal energy and state whether it is decrease or increase. So from the given data, from given problem, the stroke of an engine and heat transfer of the system. Heat transfer means it is Q is 150 kilojoule per kg, and if the work done of the engine is 250 kilojoule per kg, the work done means it is a W. W is equal to 250 kilojoule per kg. We can find the change in internal energy and the state, the whether it is decrease or increase. So the change in internal energy means we will find del U. So this is the solution part. In a closed system for which the first law of thermodynamics applies, the equation is Q minus W is equal to del U. In this problem we need to find change in internal energy, that is represented as del U. So that equation is rearranging is to del U is equal to Q minus W. Then we are substituting these values, what are the Q values and what are the W values. If indicate negatives, we will put a negative sign marks. So the final answer, change in internal energy del U is equal to minus 400 kilojoule per kg. Since the sign is negative, there is decrease in internal energy. So from these all problems, these three problems is only the application of first law of thermodynamics. Here in this problem is slightly differences from the first three problems. What is meant? It is the first three problems, the values are straightly given Q, W and del U. In these three parameters, any of two parameters will be given by the problem. We need to find that third one. But in this problem, this is fully different. For example, the parameters pressure, temperature and the values are given. We need to find what is work done or what is heat transfer and what is change in internal energy. Fine. So this is the problem. The statement is steam enters a cylinder fitted with a piston at a pressure of 20 meganewton per meter square and a temperature of 500 degrees Celsius. The steam expands to a pressure of 200 kilonewton per meter square and a temperature of 200 degrees Celsius. During the expansion, there is a net heat loss from the steam through the walls of the cylinder and piston of 120 kilojoule per kg. Determine the displacement work done by 1 kg of steam during this expansion. So, in generally the problem how to solve this, we also find given data and what are these section in to find section. Then next we goes to the solution section. In this problem the given data are the pressure values is 20 meganewton per meter square and the temperature value is 500 degree Celsius and the pressure at the X stage is 200 kilonewton per meter square and temperature of the X stage is 200 degree Celsius. In this solution, in state 1 is considered as an entry section or state 2 is considered as an exit section. These are the values of the state 1 and state 2. Closed system for the thermodynamics law applies. We know that find Q minus W is equal to del U. Rearranging the equation and the work done, W is equal to Q minus del U. So this is the Q and finally we get the work done value. Before we going to that, we will find out what is that pressure and temperature and how it you converted into change in internal energy. This is the parameters of find these problems in this given section. The next problem is application of open and closed systems in first law of thermodynamics. A mass of air is initially at 260 degrees Celsius and 700 kilopascal and occupies 0.028 meter cube. The air is expanded at constant pressure to 0.084 meter cube. A polytropic process where n is equal to 1.5 is then carried out, followed by a constant temperature process which completes a cycle. All the processes are reversible. So the first one is sketch the cycle in TS and PV planes. The second one is find the heat received and heat rejected in the cycle. And the third one is find the efficiency of the cycle. So this is the given data from this given problem. The temperature at inlet section or entry side is T1 is 260 degrees Celsius. The same pressure and inlet section P1 is equal to 700 kilopascal. It's to same as for P2 because of its constant pressure, and the volume V1 is 0.028 meter cube, and the volume at the exit section V2 is equal to 0.084 meter cube. Hence the process 1 to 2 is constant pressure process, so the P1 is equal to P2, and the process 2 to 3 is polytropic process, so the polytropic index n value is given, and the process 3 to 4, it is the final process, is a constant temperature process. These are the given data from our given problem. So the two find section is the first one is sketch the diagram of pressure and volume diagram and temperature and entropy diagram, and the second one is heat transfer Q and efficiency eta. This is the our PV and DS diagram of our given problem. Here the process 1 to 2 is adiabatic process, and the process 2 to 3 is a constant pressure process, and process 1 to 3 is a constant volume process. So similarly it shows TS diagram, what are the process in 1 to 2, 2 to 3, and the final one is 3 to 1. So from the constant pressure process 1 to 2, the temperature volume relationship is V2 by V1 is equal to T1 by T2. We substitute these values V1 and V2 and T1, we get that T2 value is 1599 Kelvin. It is the value of temperature at the section 2. The next one is the mass of the air to find for solve our work done and heat transfer. We know that gauge equation PV is equal to MRT. In that equation we need to find mass M. So we put that rearrange the equation ME is equal to PV by RT. So we substitute these pressure 1 values and volume 1 values, and R is 278 kJ per kJK. It's a gauge constant value, it's a constant, and the temperature 1 T1 value. We substitute these all values and calculating, finally we get the mass 0.128 kg. In constant pressure process, the work done formula is P into V2 minus V1. We substitute this P value is a constant, P1 is equal to P2, and V2 and V1 is in the given data. So the finally we get 39.2 kJ per kg. And the next one is heat transfer Q onto MCP T1 minus T2. So substituting these all values from our given data, Cp is specific constant at a constant pressure value. We substitute these all values, finally we get it 137.13 kJ per kg. In the process 2 to 3, for a polytropic process, we substitute the temperature pressure relation. T1 by T2 is equal to P3 by P2 the power n minus 1 by n. The substituting the T1 values and T2 values and P2 values and P3 values in the given data, finally we get the P3 value. The adiabatic index n is equal to 1.5, it is a constant value. Finally we get exit volume section V3 from gas constant equation. PV is equal to MRT. In the section is section 3, so we all are substituting the P3 V3 is equal to MRT3. Simplification this equation, finally we get it V3 values is 0.755 meter cube. The next one is a polytropic work done is work done polytropic processes, process 2 to 3. W2 to 3 is equal to P1 V1 minus P2 V2 by n minus 1. Substituting these all values, we will get it the polytropic work 78.446 kilojoule per Kelvin. So now up to we can find it the mass and work done heat transfer in process 1 to 2 and work done in process 2 to 3 and the volume of the exit section, that is V3 section. So the final heat transfer section 2 to 3 is the formula of gamma minus n by gamma minus 1 and work done of section 2 to 3. Here is the gamma is adiabatic index, it's adiabatic process, and n is the polytropic index. We can substitute the polytropic value. So we get it the heat transfer in section 2 to 3 is minus 19.612 kilojoule. The next one is a process 3 to 1. In this given data T1 and T3 are given. The work transfer of the equation is W3 to 1 is equal to P3 V3 ln P1 by P2. Here is the Q value, we get it minus 64.52 kilojoule per work output. So in this process 3 to 1, we need to find work mode of the section. Here is the basic formula of work done in polytropic process is P3 V3 ln P1 by P2. In heat received in this cycle, it indicates Qs, and heat rejected in this cycle, it indicates QR. So the positive value considered is a heat and the negative value is considered as a heat rejection. The final one is efficiency of the cycle. The basic of efficiency is equal to work output by heat input. Here is an work done by heat supplied. In this problem, the work done or efficiency in 1 minus QR by QS. That's QR, it indicates Q rejection, and QS indicates heat supply. So the final efficiency of this combined problem is 38.74%. These are the final solution of this given problem. We find in this problem, first they draw in the PV and the TS diagram of the given cycle, and the next we find work done, efficiency, heat transfer, change in internal energy of this problem. This is the application of the open system in first law of thermodynamics in aero engineering thermodynamics. Thank you. These are the problems in first law of thermodynamics application. The first 4 problems indicate the straight application. Q is equal to W plus del U. That means when a system undergoes a cyclic process, the net heat transfer is equivalent to the net work done. This is the statement of first law of thermodynamics. So the first 4 problems straightly solved the heat transfer, change in internal energy and work done. And the final problem is focus on the applications of cycles and applications of process. So that includes a constant volume process and constant pressure process and polytropic process. So in this process we also find what are the pressure and PV diagrams and TS diagram, and what is the work done and what is the heat transfer and what are the pressure, temperature and volume relation in these 3 cycle, and finally we output what is the efficiency of the cycle. So this is the process and solving procedure for applications of first law of thermodynamics.